Let's solve a quadratic inequality. Okay, so we've got an inequality here. So we want to solve this 2x squared plus 5x greater than 3. So what I want to do here, I want to just take a look at the steps from the textbook. This is on page 215. Let's look at the steps, and we're going to do the steps, and then we're going to talk about it just a little bit at the end. So first thing we want to do is we want to rewrite the inequality if we need to, where we have a quadratic function on one side and 0 on the other side. So this step's pretty quick, right? We're just going to take our original inequality, and we're just going to subtract 3 from both sides. So we're going to write 2x squared plus 5x minus 3 greater than 0. All right, so now we have a quadratic polynomial on the left side, and we have 0 on the other. So step 1's done. Step 2, find the zeros of our quadratic function and place them on the number line with 0, the number 0 above them. Okay, so we're going to make one of those little sign diagrams, right? So we need to find, so that was step 1. Step 2, we want to find zeros of 2x squared plus 5x minus 3. And we can do this. We're just going to solve 2x squared plus 5x minus 3 equals 0. And we can do this in a couple of different ways. If we really want to, we can use the quadratic formula, but it's really likely that factoring is going to be much, much easier for us. So we ought to try that. So we try it. We know that whatever is in this first space has to multiply to be 2x squared. So we know that one of them has to be 2x and the other one has to be x, because those are the only options. And now we have to choose numbers here that multiply to be negative 3. Okay, so that it works out. So we know that it's a negative, so we got opposite signs. We know that 3, the only choices with 3 are going to be 1 and 3, so that kind of takes our choice out of the deal. We want to have maybe a positive 3 over here, so we're going to get 2x times 3 is 6, and then we can have a minus 1 here so that our negative 3 is achieved here. So, and we can, multiply it out to verify it works. So 2x times x would be 2x squared. 2x times 3 would be 6x. We have minus x would be 5x, that would be that term, and then we've got minus 1 times 3 would be negative 3. So it did work, and we can solve this pretty quickly, right? We know that when we have a product of 2, we got a product, and it's equal to 0. One of those factors of the product has to be equal to 0, so that's I don't remember what this textbook calls it. Usually it's called a zero product property or something like that. Anyway, we've done this before, so we can kind of just get on with it. We would add 1 to both sides, divide by 2. Or over here, we'd have subtract the 3. We get negative 3. Okay, so now we are almost done with this particular step. We want to define the zeros, which we've done. Now we're going to put them on a number line. Here's negative 3. Here's 1/2. And so what's going on here is we're putting x values on the bottom, and their corresponding function values go on top. So if we put a 0 in here, right, if we put negative 3 into the original polynomial here, we would get a 0. Same thing with the 1/2. If we put a 1/2 into the original polynomial here, we would get 0. That's what we just showed. All right, so that was step number 2. Step number 1's done. Step number 2 is also done. All right, so 3, choose a real number called a test value in each of the intervals determined in step 2. Okay, so what are we going to choose here? It would behoove you or be in your best interest to choose easy numbers. I would probably choose maybe negative 4, and I would probably choose, 0 is in this interval, that's easy, and I'd probably pick 1. Now I'm sure that the scale is off here. Of course it is, but it doesn't really matter. All we're doing is just trying to indicate which interval these numbers lie in. And I think that's achieved. Okay, so step 3, that is finished. Boop. Determine the sign of the function. So again, we're talking about this function here. And when we're talking about just the definition here, this is the quadratic that we're calling f. Okay, So we want to determine the sign of our function for each test value in step 3. So we're going to use these values, -4, 0, and 1. And we're going to write that sign above the corresponding interval. So maybe I can do step 3 in blue, step 4, let's do this in, I don't know, is this pink? Looks kind of pink from where I'm standing. Sitting? In pink. Okay, so we're going to do this. We want to just determine what the sign is. So we can do this by maybe just plopping it in. I just underlined something up there. We can do this by just determining the sign by plugging it into here, right? So if I put -4, in there, I'm going to write this, just so I don't have to keep going up and down with the paper. Okay, so we're considering this to be our function, right? And we want f of -4, and all we care about is the sign, right? All we care about is the sign. So if I put in a -4 into this piece, we would have 2 times -4, that's -8, -1 would be negative, right? Okay, so then we'd have -4 in there, -4 plus 3, that's negative. So this would be a positive, right? So we're going to write that that's positive up there. So we're doing this step 4 in pink. We're putting positive up in that interval. Okay, now we want to test our next one. So we got f of 0. This will be pretty quick, right? If I put 0 in here, I've got 2 times 0, that's 0, -1, so that's a negative. And then if we put a 0 in here, I've got 0 plus 3, that's positive. So now negative times positive, that is a negative, negative. So then we can put the corresponding value here, okay? And now we've got our last one, f of 1. So f of 1, I'm going to put 1 in here. So we've got 2 times 1 is 2, -1, that is positive. 1 plus 3, that's positive. And the net result is positive. And again, all we really care about is just the sign of these things. We don't care exactly what the value is. We just want to know whether or not it's positive. Okay, so that was step 4. Now let's take a look. Step 4 is done. Choose the intervals which correspond to the correct sign to solve the inequality. So we should go back and look at our original inequality. Well, maybe not the original inequality, but what we had after step 1. So after step 1, we have that we wanted our polynomial to be bigger than 0. So that's not equal to 0, that's just strictly bigger. So when we go down to our little test intervals here, we just want the intervals for which the value is positive. So we can see pretty quickly that it's here and that it's here. So everywhere to the left of -3, these values are positive. For every value to the right of 1/2, these values are all positive. So we can say what our solution set is here for step 5. So we want our function strictly bigger than 0. So the solution is, well, it's the set of all the numbers in these intervals where it's positive, right? So we want everything to the left of 3, which would be -infinity all the way to 3. And we don't include 3 here because it's strictly greater. We want it to be strictly greater, not equal to 0, but strictly greater. So we've got this interval, which is here, right? -3 and left. And we also want 1/2 and to the right. So we've got union 1/2 to infinity. All right, so there's our solution set, and we just followed all the steps. Let's talk just a little bit about what we're doing in just a little bit different way, maybe. So graphically, why this is working is that when we're here, we want to know where is this function, which we know if we drew a picture of this, it's a parabola, right? So when we wanted to know where is the parabola above 0. That is, where is it above the x-axis? So thinking about these graphs, we can cross the x-axis at exactly the zeros, right? So the only places that this parabola could possibly cross the x-axis are at x equal 1/2 and x equal -3. If we drew a picture of that, we've got x equal -3 here and x equal 1/2 here. So if we were going to go and draw a picture of our function here, this, well, it could be boxing here as well, right? So if we're going to go and draw a picture of our parabola, it's of this parabola, it has to have these x-intercepts, right? So then we can further think about what the picture of this looks like. Well, it's got a leading coefficient that's positive. That means it opens up. So if we're going to draw a really rough sketch of this, we don't know exactly where the vertex is, but we do know that it opens up because the coefficient is positive out front. Okay, so now what the heck is going on with this? If we just drew the graph, we could just immediately say what the solution set is by drawing the graph, can't we? Because we found these zeros, we wanted to know where is the parabola above the x-axis. Well, it's exactly to the left of -3 and to the right of 1/2, right? It's this branch and this branch are both above the x-axis. Well, hopefully that helps you understand why it is we're doing this. In the future, when we do this with polynomials in general, the idea is the same, but we can't exactly take this shortcut up here by drawing the picture because we don't necessarily know exactly what shape a polynomial of arbitrary degree is, right? If our degree is 7, it might not look like this, and we should take that into account. We were just showing how this worked with a parabola because we already know what the graphs of parabolas look like. So hopefully we are in good shape as far as putting those two ideas together. Again, either way, our solution set is that.